Hello, and welcome to the video for 1.6, where we are talking about measuring center. So we're looking at a data set and trying to be able to describe like the center of it. What's like its typical. So we've talked about center before, and we looked at center as a median a lot of times because that was like the easiest thing for us to find. But there's actually like multiple ways to describe the center of a data set. So first, I kind of want to like describe more what I mean by when I say like center. So the word center itself really talks about like the middle. So if we kind of put all our numbers in the data set in order, we're trying to see what's in the middle. Or another way to describe it is like what's something typical, like a typical way to describe your data set. So is there a number that you can use to kind of summarize all the numbers that you have in the data set? So that's what we are looking for when we're talking about a center of a distribution. So one way to do this is with the median. So we've been finding the median, we've been describing it as the middle number of our data set. So the only thing that changes is if there's an odd number of data points that you have in your data set, then you just find the middle number and that's it. That's your median. But if you have an even number of data points, then you would end up with two numbers in the middle. So with those two numbers, we need to find the average of them, and that becomes our median. So when we find the average of something, we add them together and divide by 2. So, what does this number mean when we actually find the median? Whatever number we get for the median, we're saying about half of the data points that we have, the numbers of themselves are above that. So, half of your data set is a number above the median, and half of your data set is a number below the median, whatever your median number might be. And one more nice thing that we like about using the median as what we describe as the center of our distribution is that it's resistant to outliers. What I mean by that is outliers aren't going to affect whatever number you get for your median. So if you think about it, when you have a data set, and let's say you have some really big numbers in your data set that are outliers, just really far away from the rest of your numbers in the data set. So when you put them in order, they're going to be at the end because they're really big numbers. But when you count towards the middle, the median doesn't change because whether or not you have really big numbers at the end doesn't really change what the middle number is going to be. So that's what we mean when we say resistant to outliers. Resistance is talking about whether outliers would affect it or not. Okay, so the next way that we can describe the center of a distribution is the mean. So the mean is really just an average. So hopefully you remember how to calculate the mean. But I do want to introduce a new symbol. So x with a little line on top, we read it as x bar. So x bar is the symbol that we use for a mean. Anytime we calculate a mean, we say x bar equals and then whatever number we get for our average. So just in case you forgot the formula, x bar, our mean, equals if you add up, so sum all your data values together, and then you divide by n. I call it n, where n stands for the number of data points that you have. So add all your data values up, divide by how many data values that you have. And that's the formula for the mean. So we said x bar is the symbol that we use for the mean. The median does not have its own symbol. We just write out median equals whatever. So no fancy symbol for it, but for the mean we do. With the mean, it is not resistant to outliers. So earlier we said resistant to outliers is that when outliers don't actually affect whatever your number is going to be. With a mean, it is not resistant, meaning the outliers will affect your mean, because when we sum all of our data values together, when we add all the numbers up and then divide, if you have really big outliers, then when you add everything together, you're gonna get a much bigger number because you have really big outliers. So when you calculate your average, it ends up affecting and making your mean a lot bigger because you have big outliers. And vice versa, if you have really small outliers, then your mean will be a lot smaller because you have some really small numbers in your data set. Alright, so now let's take a look at both the mean and the median together. So when we have a data set, we can graph it out, make a dot plot, a histogram, whatever. If the graph ends up being a certain shape, the mean and the median would get affected, and here's how. Let's say we had a dot plot that was perfectly symmetric, so obviously you can see on both sides of my dot plot, it is perfect mirror images on the left and right side, so this is a symmetric graph. When this happens, if we were to find the mean and the median, then the two numbers would be equal to each other. Because if you think about it, median is your middle number. So when we count towards the middle, it would just be right here. If you find the mean, you have an equal number of small and big numbers. And so when you add everything together and divide by how many there are, you're just going to get the middle number. So anytime the graph is symmetric, the mean and the median number become the same. Okay, next, if your graph is skewed to the right, so remember shorter bars on the right side, then the mean is going to end up being greater than the median. Because, so first, when we find the median, this is just the middle number, so I would count towards the middle, and it would be somewhere over here, because I've got about half of the data above and half the data below. But when I calculate the mean, I have a few big numbers, but kind of generally more smaller numbers, but those few big numbers, kind of like the outliers, will increase my mean by a lot. So the mean always ends up towards the tail of the graph. Wherever the shorter bars are, the mean always goes towards that direction. So the mean ends up being bigger than the median, so greater than median. And then if it's skewed left, the opposite is true. So the mean ends up being less than the median when it's skewed left. Same exact reasoning, but just switched. Which means that anytime you're trying to use the mean to describe the center, it works the best when you don't have skew, you don't have any outliers in your data set. So if you have a graph that's skewed or you have outliers in your graph, then you want to use the median, because then the median is when it's resistant to outliers, and outliers won't affect it, any skew won't affect the median. Okay, one last example. So here we see a graph, like how long it takes to travel to work or something. So looking at this already, we can see that the graph, our distribution of our data set, is skewed. I've got a lot shorter bars, and it kind of looks like outliers even on the right side of the graph. So this would be a graph that's skewed to the right. So if it's skewed, then the median would be the best way to measure what our center is of this data set. But just so we can compare, we're going to find both the mean and the median, and then decide which measure of center is better. So let's start by calculating the mean. So we said x bar is the symbol for mean, and we are going to be adding up all our numbers in the data set together on top, and then on bottom we're dividing by how many data points that we actually have. So our data points, it starts on this dot plot. It looks like this is a 5, this is a 10, 15, 20, and so on. So we are adding together 5 plus 10, but there's 2 dots at 10, so I'm going to add 2 10s plus, and then we have 4 15s, so 15 plus 15 plus 15 plus 15, and keep going all the way through all of your points. If you notice, since like we have 3 20s for the next one, you can do, because you know we are mathematicians and kind of lazy, since I know that I'm going to be adding 3 20s together, I can just take 20 and times it by 3. And then I have a 25, there are 2 30s, so I can just take 30 and times it by 2, and so on. And counting up how many dots I have, because that's how many data points I would have, there are 20, so I'm going to end up dividing by 20. So when I add up all my data points together, I end up getting 625, and we are dividing that by 20, so I get 31.25. So I know here we're talking about minutes to travel to work. For averages, sometimes we're talking about like people, like the average number of people or whatever. Even though it's not a whole number, averages are allowed to have decimals, even when we're talking about people. I know like people, we can't really have like 0.25 of a person, but when we're dealing with averages, you still want to keep the decimals there, because we're telling people like this is the number that would be the best to describe the typical travel time or whatever. So you want to include the decimals, even though sometimes it doesn't make sense in terms of like whole number people, things like that. Like time to travel to work, the decimals are fine. But anytime we deal with means, averages, we always keep the decimals. Alright, and then to calculate the median, just like what we did before, we're just counting towards the middle to see what the middle number would be. So, just like before, we can kind of count towards the middle. You can cross stuff out if that helps you. So continuing to do this all the way until we get to the middle two. In this problem we said we had 20 data points total, so that's an even number, so you should end up with two numbers in the middle. So this looks to be 20 and 25 as our two middle numbers. So if we have two middle numbers, we're supposed to average them out. So I'm taking my two middle numbers of 20 and 25, adding them together, dividing by 2. I end up with 22.5, so that's my median. Okay, so earlier we were saying this graph is skewed to the right because I've got outliers, I've got much shorter bars on the right side. And so earlier we said when it's skewed to the right, the mean is supposed to be greater than the median. And if we look at our mean and median, yes, the mean is greater than the median because the median ends up being kind of closer to like the where more of the data points are. Because remember, median is like talking about 50% of the data being below it, 50% being above it. So if you have fewer points on one side, then the 50% will be like much more spread out. So the mean though, because we're adding in a bunch of like big numbers over here, this drags the mean to be a bigger number as well. So that's why our mean is bigger than the median. So which measure of center better describes a typical travel time to work? Explain your answer. So here, we said because our graph is skewed, we have outliers, the median is the best to use because if it was the mean, we would want a symmetric graph with no outliers. So this is the median would be best, and it also makes sense because if most of our values in our data set are kind of towards the smaller end, so like somewhere between, 5 and 30, then our typical number used to describe our data set, we also want to be somewhere over there, between 5 and 30, which makes more sense with the median because we got 22.5 from that. But the mean of 31.5 is like slightly out of that range, and it's like really influenced by these really big numbers here, which isn't the typical number in our data set. So my answer, median is best to describe the center because the data is skewed and has outliers. That would make our mean too high, so the median is best. Alrighty, so that's it for this section. Not too long of a video. Go ahead and do the classwork. Thanks for watching. Don't forget to like and subscribe. Just kidding, you don't have to.